Okay. Then let's talk about some things we were talking about before. I want to talk about a couple memorization things in the class. So first off, talk with my other colleagues, and you do need to memorize solubility rules. So I will not give you the table. Let's go ahead and grab that table real quick off the previous notes, though, and talk about it. So I'll grab it so we see it. No, that's not right. There it is. Okay, so here are solubility rules. Here's the table, but before you look at it and go, oh, I've got to memorize all these different things, it's sort of easier when you use the periodic table, right? So everything in this column is soluble, right? Not the H. Well, yes, the H. But everything in this column, so if you look at that bottom, now everything in that column was the top part, everything in this column, this is the top of the second line, so second yellow line right below, all those, except you have a couple exceptions here. You've got lead and silver and mercury. Okay, so you need to memorize those exceptions, but you've got those two outer columns there. And then we have a number of ions here. Well, really, you've got ammonium and nitrate, right, in terms of what I would ask you, because what about the chlorate and the perchlorate and the acetate in here? Anybody remember anything about those? Anybody remember anything about ammonium and nitrate? I told you you had to memorize those, right? I told you you didn't have to memorize these, so you don't worry about those. Okay? And then sulfate you do need to memorize. There's a mess of exceptions there. Yeah, memorize sulfate. Don't worry about the exceptions so much. Okay? That makes sense? So I'm not going to have you worry about the exceptions for sulfate because I don't see a nice pattern there. So we're going to cross off these in terms of what you need to memorize. And we're going to cross off these for what you need to memorize. And I'll make sure everything's realistic, but avoid those. I'll avoid these. I'll avoid these. Okay? So that's what you need to do from that. In terms of, but while I've been working my way through lecture notes, doing your homeworks and things, so I've told you that there are a series of polyatomic ions you need to memorize, and those keep coming up, right? So they're not going away. They're going to keep coming up throughout the course, and so you need to get those memorized if you don't have those memorized yet. So they'll certainly show up in that next exam. Let's remind you what those are. So nitrate, hydroxide, we've got sulfite. Yes, sulfite. We've got sulfate. We've got nitrite. Phosphate. Ammonium, like I already said. How many is that? There are 9. 1, 2, 3, 4, 5, 6, 7. We've got to come up with 2 more. Carbonate. And bicarbonate. Okay, so I've already assumed you've memorized these. I haven't actually assumed that, but you were supposed to memorize these, okay? All right, just because I'm having you memorize these doesn't mean that in the homework problems you see out of the book, because I just grab whatever the good homework problems that are there. I don't have like 100 homework problems to choose 10 from for most topics. You might see these polyatomic ions, so you should recognize them if you see a bunch of ions together for doing your homework, but you of course can look at your book and things for doing those things, right? Okay, so you sort of need to know they exist, and your book certainly likes acetate. I've seen acetate a whole bunch, but you don't need to memorize acetate in terms of quizzes and tests. Questions on memorization there? Okay, so what we got was we had this. So we have to memorize this table outside of what I've crossed out. All right, and then you need to memorize these 9 ions, which we already knew about. And nothing else for now. Outside of the various concepts that we're using. We have various types of reactions and such. Okay, questions before I go on? Okay. So we're going to talk about some new reactions today. We're going to talk about acid and base reactions and the neutralization reactions. So acids, bases, and neutralization reactions. Acids, bases, and neutralization reactions. So we, in chapter 4, they introduced acids. So we're going to we skipped that, so we're going to introduce that right now. So when I talk about an acid, acids produce H plus in water. Okay, so they produce a hydrogen cation. Remember, cations are positively charged ones. Let me get the chart. Let me get this superscripted like it should be. All right, so for example, you've probably heard of hydrochloric acid, okay? Hydrochloric acid looks like this. This is the main acid that's in your stomach. Fairly concentrated in your stomach. Obviously, it doesn't burn through your stomach. And so this will dissociate in water, okay, just like our salts do, to make H plus and Cl minus, okay, or chloride ion. All right, so that's what we mean by it produces it in water. If I put this in water, it's already in water over here, it's being aqueous. But in terms of this equation, I'm trying to decide. You can get this as concentrated. Well, you can get this and burn your face off concentrated, but I think it still has some water around. Okay, so I don't know that we ever get it where it's not aqueous, but when we get it and we dilute it out in water, that happens. We can also think, here's another acid. This is sulfuric acid. Okay, sulfuric acid you can put into water and it will dissociate. To make a sulfate ion. Let's not forget the charge there. A sulfate ion and a and 2 H plus ions. Okay. You guys see how that works? All right. We'll talk about this more. We'll talk a lot more about acids later on. But for today and for this chapter, we're just concerned with neutralization reactions. Questions on that? Where are the H's when we talk about something being acidic? Do you see where the H's are? They're in front, right? So if I think we've also had other compounds that have H's. So here's methane, right? We can talk about methane gas, right? We put methane gas into water. First of all, it's not very soluble, right? But we could put it into water. We could get it into water, sort of. This seems wrong. Let's do this. Well, let's not worry about the phases here. But this is not an acid. And it's because these hydrogens are not listed first. If the hydrogens come off in water, they're listed first. Okay, a better one for kind of showing this with the phases, and I show it dissolving in water. I'm reluctant to show methane gas dissolving in water because it's nonpolar, it doesn't dissolve well in water. But we could talk about something instead like glucose, which is the sugar that's kind of running around your blood, powers your brain, powers other things, but your brain almost exclusively runs on glucose. So we could take this glucose and we could dissolve that in water, and it actually does dissolve in water. Okay, it's a molecule. It is not ionic. It's made up of all, how do I know it's not ionic? It's made up of all what? It's all nonmetals, right. It's all nonmetals, so I know it's not ionic. That will dissolve in water quite well, but the H pluses don't come off. We don't get H pluses off because they're not listed first, right? It has to do with the structure, okay? But we'll not worry about that structure for a while. And in fact, I don't know whether we'll cover it here. You'll get it if you take organic. Certainly in organic, you explain more of why. Questions? Okay. So then we have bases are going to produce OH in water. That's called hydroxide. That's one of our ions. Okay, and so it's OH minus. And so what we think about is something like sodium hydroxide, right? Sodium hydroxide is a solid. We can get it up in the stock room. It's actually very dangerous because it's very corrosive. And it will break up to make sodium ions in water and hydroxide ions in water. How from my solubility rules do I know that it does this? This is the easiest solubility rule on that table to remember. It's an alkali metal, which is I actually don't even know my name, so you know your names. That's great. It's the left-hand column, right? Everything in the left-hand column is soluble in water. So if you make anything that has a sodium, a lithium, a potassium, a rubidium, a cesium, a francium, any of those things in that column, regardless of what the anion is, they're going to dissolve and break up in water. Easiest rule on that table. Easiest rule on the solubility table. All right, and so I can also do lithium hydroxide, right? And we're going to get the same sort of thing here. And I've actually avoided doing more complicated ones with hydroxide because it's hard to find other hydroxides that are soluble in water. Okay? So if you remember from your table that you need to memorize up here, and I'll be right back down, there's no hydroxide ion on here, right? So if something has hydroxide ions and it doesn't have one of the metals up, one of the things up here to help make things soluble, it's insoluble. Most hydroxides are insoluble. So everything in that second column, beryllium, magnesium, calcium, strontium, barium, all those things are insoluble as hydroxides. Aluminum hydroxide, insoluble, not soluble. Okay, does that make sense? All right, so hydroxide's not on this table. You see a hydroxide, probably not soluble unless you've got that left column. Anyway, that's why I'm not doing some of them. All right, although you could do neutralization reactions with them. That is something else. All right, so now let's talk about neutralization reactions. So in neutralization reactions, we have an acid reacts with a base to make water and a salt. An acid reacts with a base to make water and a salt. And when we say salt, I mean an ionic compound. All right, so if I was to just write that out, I'm just going to write acid plus base, water plus salt. And so I'm going to interchangeably use ionic compound and salt, and I will probably switch over to saying salt because that's how most chemists say it, because we're lazy and salt has one syllable in it and ionic compound has three. Okay, so let's talk about that. Let's take one of these reactions from above. I could take one of my acids from above. Let's go ahead, and I had hydrochloric acid was one of my acids up above. All right, so I could have hydrochloric acid and I could have sodium hydroxide. Okay, we're going to say they're in water. All right, not that they're solids. So you've got a sodium hydroxide solution. It's dissolved in water already. And if we do this, this is a double displacement reaction, but because it's got an acid or base, we give it a special name for neutralization. Double displacement, I'm going to swap partners. So the chloride's going to go with the sodium, and the hydroxide's going to go with the H, right? The H, that's going to be an H plus. And so this is going to become HOH, otherwise known as water, right? Just in terms of seeing those things. And then sodium hydroxide. No, not sodium hydroxide. Sodium what? Chloride. Thank you. Okay. All right. And I'm going to take my HOH. I'm actually going to swap these because you should write water. But remember that that's HOH. You guys see that? Okay. So this is our salt right there. What kind of equation is that? Molecular, complete ionic, partial, or net ionic? Which one did I write? Molecular. The molecular equation is where I keep everything together, right? This is molecular. All right, they're all aqueous, right? All aqueous except for, I'm sorry, that water shouldn't be aqueous. We're going to write water as liquid. Okay, they're all aqueous except for water. Go ahead and write the complete ionic equation for that. So what's the, when we do an ionic equation, any ionic equation, what do you do with it? Yeah, you break up the ions, right? So they're all broken up, and you write aqueous next to each one. Yes? So good question. Remember, when you break them up, you label each ion as aqueous. Okay, if it's aqueous, you break them up, and you label each ion as such. Go ahead and take 30 more seconds on that, and then we'll go ahead and write it out. And if you've already got it written down, that's great. Otherwise, please take advantage of this time in class to practice these. Okay. All right, so I'm going to write the net ionic equation. I take this hydrogen chloride here, right, the hydrochloric acid, and I'm going to make an H plus a Cl minus. Both are aqueous. Plus, I'm going to break up this sodium hydroxide because it is also listed as aqueous. So a sodium plus aqueous plus an OH minus, or a hydroxide minus. I guess I shouldn't say hydroxide minus. It's implicit. If I say hydroxide, you know it's minus. Then I've got my water, which is not aqueous, right? It's a liquid. So we'll leave that together. Then we'll take sodium chloride over here. Sodium plus aqueous plus chloride minus aqueous. Okay? And this is a complete ionic equation. Okay, complete ionic equation there. All right, what here are the spectator ions in this complete ionic equation? The spectator ions, if you remember, are the ones that are the same on both sides, right? So if we look at this, do I have H plus on both sides? No. Do I have Cl minus on both sides? Yes. Do I have Na plus on each side? Yes. Okay, do I have OH minus on both sides? No. Okay, so these are my spectator ions. So let's do a little key over here. Spectator ions. Okay, and so if I was to write the net ionic equation, what would this look like? Write out the net ionic equation. Remember that the net ionic equation is just the complete ionic equation minus the spectator ions. Okay, so what have I got left here? I've got H plus, right? Plus OH minus makes water. So my net ionic equation is just going to be this for a neutralization reaction. Right, and I've got to go back and make sure I get my phases in here. So it's going to be H plus aqueous and hydroxide aqueous react to make water. And any net ionic equation for a neutralization reaction is going to be that, because the other ions are going to be soluble. Okay? So I'm pretty much never going to ask you to do a net ionic equation for a neutralization reaction. Okay? Questions? It's possible. Sometimes you could have a solid, like I could have a solid base and I'd add my acid and the acid would kind of eat away at the solid. So possibly we would see it, but mostly it's pretty boring. All right, let's try another one of these. And we'll try one that's more complicated. So we'll take that sulfuric acid. All right, so aqueous plus, I'm going to react that with, I don't know, let's react it with lithium hydroxide this time, aqueous. All right, let's just do the molecular equation for this. I want you to complete and balance that reaction. So complete and balance the following reaction. Okay, I'm looking at folks, what some people have, and so you've got two H's on the sulfate, right? But they make two H plus, separate H pluses. So you're not gonna make H, they don't travel together. Okay, it's individual H pluses, so you're not gonna make H2OH. You're gonna make H2O. Remember, neutralization reactions make water and a salt. Go ahead and try that. I'm glad we did this one. We'll get that out of our system. So. All right, so I've got a neutralization reaction here, and I'm going to make water because it's a neutralization reaction, okay, which is HOH. So I've got these H's over here, but they don't travel together. They become two H plus, not H2 like that. So, and then I'm going to make a salt. So my salt is going to be lithium sulfate. So Li2SO4, right? Now I need to balance this equation. All right. So this is a great practice balancing equation for us here. It's great for us to practice because what's going on here is I've got lots of stuff going on. This is like maybe one of the more complicated ones we would have. I have oxygens in multiple substances on each side of the equation, right? Okay. And I also have hydrogens in multiple substances. Now these sulfates, these four oxygens travel together. Okay, so that might help you, but you don't really need that to do it. So what I'm going to do is I'm going to look at this And I'm going to balance my sulfurs and I'm going to balance my lithiums first. I see that I have 2 lithiums over here, right? How many lithiums over here? Okay, I'm going to put a 2 in front of that to fix that one. And then now I've fixed my sulfurs, right? Now I have 2 lithiums. I have 1 over here. I fixed that as a 1. I could put a 1 in front of it for now, and I'll erase it maybe. So now I've fixed, remember, sulfurs to be that, right? So all I'm left at, so this is 1 sulfur over here. I've got 1 there. And let's see if I can balance the rest of it by just changing the number in front of the waters. I know those 4 oxygens go with those 4 oxygens, but I can still count them up. I have 2 oxygens here in front of lithium. I have that. I have 6 over here, oxygens total. I have 4 oxygens here. Let's actually write those out. Let's write those in the bottom. So I have 4 oxygens in this compound, right? Over here, I have 2 oxygens here, and I have 4 oxygens here. When I look at the numbers, do you see why I have 2 oxygens for the lithium hydroxide? Anybody have a question on that? Okay, so then this is going to be, I'm going to need to get 2 oxygens out of the water. Do you see that? So it would be this. Okay, at least that's what I think. I'm going to check it by going back because I never balanced the hydrogens, right? Let's just check the hydrogens, and if I got the hydrogens correct, it's probably okay. I'm going to erase my 1s. But so I've got 2 hydrogens here, and I've got, 2 hydrogens here, right? And 2 more hydrogens here for 4 hydrogens, and I have 4 hydrogens. All right, does anybody see any other mistake I made? I could check all my atoms, but I'm thinking since my hydrogens worked out, I probably got it right. If I was doing this on a test, I would check all my atoms if I had time, and if I didn't have time, I'd just check the hydrogen and move on, depending on what my time was like. Questions on neutralization reactions? Okay. All right, so we saw that important thing that if we think about, so remember these come from our complete ionic equations, which I'll draw out the complete ionic equation for this here because I want to emphasize that those 2 hydrogens on the sulfuric acid don't go together. So I've got 2 hydrogens. If I was to write a complete ionic equation here, it would look like that. 2 would come off. I'm going to go back and I will, I'll add my phases in a second. I'd have 2 lithium plus 2 hydroxide minus is going to go across, and it's going to make me 2 waters. And those, I'll leave those as a liquid right now because those are going to stick together, plus 2 lithium plus sulfate 2 minus, which I missed my minus on the other side. Can't forget that. And this is aqueous, and this is aqueous, and this is aqueous, and that's aqueous, aqueous, and aqueous. Okay, questions? So the real point there, and the mistake that many people made in terms of this is not, it does not exist as, I'm sorry, it doesn't break up as to make H2 plus SO4 2 minus, okay? Not that. Does that make sense? Okay. So when you have extra protons, you have more than, extra hydrogen pluses, we'll call them protons soon enough. But when we have extra H pluses, they all become H pluses, they don't stick together. Any questions before I move on? We're going to talk about oxidation and reduction reactions next. Okay. So we have oxidation and reduction reactions, and these are really cool. The ones up above are cool too. All right, in oxidation and reduction reactions, electrons are transferred between compounds. Ions are compounds.
I'm going to say between elements, ions, or compounds. Okay, and we're going to start off looking at metals. All right, so we're going to talk about solid metals. We've had problems that have solid metals in them before. And so one example of this, a common example people talk about, is zinc. So we can take zinc solid plus copper sulfate, and that's going to be aqueous, goes to make zinc sulfate, aqueous, plus copper solid. Okay, and this would be our molecular equation. All right, when we look at something like this, whenever you see a solid metal, what that tells you is that the oxidation state, so that tells you the charge. Let's look at the charges. The charge, let me put it over like it's a table. The charge on that metal is 0. Whenever you see a solid metal, it's 0, okay? The charge on the metal ions in this are 0. Okay, so this copper is also 0. However, this copper is with a sulfate ion. Does anybody remember what the charge is on the sulfate ion? It's 2 minus. So for this to be neutral, if this is 2 minus, what's this have to be? 2 plus. So this is going to be 2 plus. All right. And then what's the charge need to be on this zinc if it's got 1 sulfate? 2 plus. So effectively, what's going on in this reaction is we have zinc, right? Zinc has all its electrons, so it's got that, what do we got there? We go like 10 across the middle, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then plus 2, 12, right? It's got 12 electrons in that, well, I'd say outer shell. These are the 3 Ds here, right? Really what's going on here is this is our outer shell, right? These are here, but they're 3 Ds, and when they're full, we don't count them. Let's not worry about that. We can think about we have 12 here, all right? We've got 12 here, electrons, and then how many does it have here? So let's talk about number, electrons, outer shell. So zinc here, we said we had 12, right? What happens when we go to plus 2 if we had 12 before? It's going to be 10 electrons, right? Because you have to take 2 away to make it more positive, right? We're taking negatives away to make it plus 2. Does that make sense? And then the the copper in the plus 2 state has how many electrons in that outer shell? Let's not worry about that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, right? Has 11 in its outer shell when it is neutral, when it is 0. Okay? And then when we go to plus 2, how many would it have in its outer shell? We have to take how many away to make it plus 2? We have to take 2 away to make it plus 2, so now it is 9. Okay, so do you see what's happened here is when we go from left to right across this equation, that 2 electrons come from here. Essentially, 2 electrons are coming from this zinc, and they're going onto the copper to make the copper a solid. Okay, and now zinc has 2 less, and that's why it's plus 2. want to show you how, I wanted to do this to show you how the electrons are being transferred. I am not as concerned that you could do this formula, okay? This line, yes, the charges. You need to be able to do that charges, okay? All right, let's go ahead and write the complete ionic equation for this. So the complete ionic equation is going to have zinc solid, right? It's not aqueous, so it just stays that way. Copper sulfate is aqueous, so what do I do with that? I break up the ions, right? Copper plus 2, aqueous, plus sulfate, aqueous. Two minus. And then over here I have zinc. Sulfate is aqueous, so I'm going to break that up. Plus sulfate aqueous. Plus copper solid. All right. Once you've written that down, go ahead and underline on your page the spectator ions. All right, so we've got our complete ionic equation. It has spectator ions. What are my spectator ions here? Taylor. It's the sulfate. Right? Sulfate is our spectator ions. So now if I write the net ionic equation, it turns into zinc solid reacts with copper, not fluoride, with copper that's dissolved, so aqueous copper, to make zinc that's aqueous, plus copper solid. Okay? So all we see is the action here. We see the 2 electrons get transferred to this copper to make copper solid, and now our zinc is dissolved. Questions? Okay. Whether that happens, so we can do that with other examples, and we will as we have time in the next 15 minutes. But whether that happens, there's an activity series, right? So just like when we talk about electronegativity, and the activity series is not based on electronegativity, but we talk about electronegativity and how atoms want to have the electrons more, right? Well, there are different metals want to have more electrons more than other metals, okay? So what we say is, and we have to have a term we talk about this, so we talked about this being oxidation and reduction reactions. So copper got electrons. Copper is reduced. We say it's reduced. The charge went down, right? The charge became less positive. It was +2, and now it's 0. It was reduced, okay? Oxidized isn't as easy. So then the zinc has been oxidized. All right, it has lost electrons. I'm going to give you we're not quite there yet, but I think now is a good time to talk about it, just in terms of this concept. We talk about oil rig. I don't know if you've seen this before. Oil rig. Okay, there's also one that involved a lion, Leo the lion, but I don't do that one. So oil rig. Okay, so we got oil rig written like that. Oxidation involves loss of electrons. Reduction involves whoops, gain of electrons. Okay? You can remember that for the rest of your life, at least until you'll never see a chemistry test again, okay? Or chemistry on a test again. So if you're pre something health and you're going to have a big scary test that will have some chemistry on it in the future, you'll definitely want to remember oil rig and a lot of other stuff. But oil rig's a great thing for that. All right, so up here, copper was reduced, it gained electrons, right? Zinc was oxidized, it lost electrons. All right, so which metal will react or give its electrons to another metal is determined by, we have an activity series for this. So this is your book. This activity series actually comes from something more complicated that we're probably going to be learning in second semester general chemistry. But here I'm going to blow this activity series up, and it just kind of shows you, it talks about the reactivity of these various metals here. All right, so what we start out with is we have the super reactive metals up at the top, lithium and potassium. Okay, these are so reactive that if you put them into water, these react with water. All right, so these are so reactive that if I put lithium in water, it'll kind of go in and it'll kind of spin around. Okay, it'll spin around in water, and fizz and things like that, and it gives up its electrons to water. And then potassium actually is so reactive that it reacts really violently with water, and you will actually get stuff starting on fire. So it'll make hydrogen gas at the same time, and then it'll ignite that hydrogen gas. I used to do these demos in class, but I went shot a piece up into the ceiling, and they don't let me do those anymore. But it is really cool stuff. So watch some videos on the internet. Sodium, potassium, lithium. You'll probably have some YouTuber going nuts about, okay, now I'm going to do cesium. I'm going to blow up the world. But I mean, it does react really, really violently, but not going to blow up the world for that. So these other ones, actually, these will react with acidic water. But you have to put acid in to help. Okay, so this is just regular water. You actually have to be careful with some of these, actually, in terms of if it's really humid out, even if you've got the top ones here. Cesium, I'm sure you have to worry about it being humid out. Okay, but and essentially what we've got here is these are most reactive at the top and they're least reactive at the bottom as we go down. All right, and so this is, so gold, is very valuable. Platinum, you've probably heard, is very valuable. And part of why these are valuable, they're valuable because they're pretty, right? They're used in jewelry and things like that. But you can go and you can get gold jewelry from ancient Egypt, and it looks good, right? You go to the museum, and they've got their gold things, and the gold stuff all looks great, right? When's the last time that you went to a museum and you saw an ancient old iron axe? Or iron anything that looks good. So whenever you don't see iron generally, and if you do see iron, it's generally kind of corroded and things like that, right? That's because iron is more reactive than gold or platinum. Okay, so this reactivity matters for things, and it turns out that gold and platinum are useful on an industrial basis. So platinum, anybody know where you can find some, actually it's palladium. Is it palladium in your catalytic converter? Anybody know? Or is it platinum?
It's palladium.
It's palladium, okay, not platinum then. But palladium's number 46 and platinum's number 78. If you look at the periodic table over here, they're both in group 10. What do you think about the reactivity of platinum and palladium? Similar. Yeah, similar. So palladium is also not going to be super reactive. So palladium provides a surface for reactions to happen on in your catalytic converter of your car, but it doesn't break down easily, which is important because it's being exposed to really hot gas. Okay? Hot and reactive gases. Questions? Okay, so we're going to use this activity series here then to answer whether things are going to react or not. So let's say we have, so we'll go ahead and say we have iron solid. So I got asked a question about this after class the other day, but that's related to this. So I have iron solid and I have aluminum 3+. Okay, what is going to happen here in terms of our reactivity series? So, and then we could make iron can be 3+. Let's make it easy, okay, in terms of balancing things. So to make aluminum solid. So the way we use this activity series is, will iron give up its electrons to aluminum? All right, so when we think about our activity series here, I'm going to actually make this smaller. If you have a computer and you want to bring up your book, this is in, I think, section 5.5. I need to be able to get enough of this on here that we can talk about it. And then we talk about reducing strength. Reducing strength means more likely to give up electrons. More likely to reduce something else. All right, so what have we got on here? I've got aluminum up here and I've got iron up here. These are more likely to give up electrons. Which one is more likely to give up electrons, iron or aluminum? Aluminum. So the way we use this table, aluminum, remember, aluminum is more likely to give up electrons. So aluminum is more likely to give up electrons, which is this direction, right? Giving up electrons, becoming more positive. So does this reaction happen? It doesn't. This reaction does not happen. All right, so what we would do here is, let's go ahead and say activity table tells us aluminum is more likely to give up electrons. Yes. I really hope not. I have to go talk to my colleagues, and I'm going to argue that you do not need to, as opposed to more like last time I kind of asked. So let's say for now, no. And it won't be the whole table. Okay, let's take another one. Give me so I'm gonna go copper solid. Give me another metal. Give me a random metal. Actually, go ahead. What, silver? All right, so let's do silver. So we have silver, right? That is, actually, that's a great choice. Thank you. So we've got silver, right? That is an ion, so it's aqueous in water. And then copper, actually, this works really well because copper actually does have a +1 state, so we can do this. You don't need to know, well, you do need to know copper and iron, but to make silver solid, right? So which one is giving up the electrons here? Which one of these is giving up the electrons as I go from left to right? The copper, because the copper is becoming more positive, right? So what we want to see on the table is that copper is more likely to give up electrons for this reaction to go. So if we go up to our table, we've got silver right down here at the bottom, right? Copper isn't bad either. This is also why you can, sometimes see copper tools in a museum. right? It's better with bronze, actually, it becomes more stable. But you see, so silver, copper is more likely to give up electrons, so we can do our reaction. Here it's actually going to copper plus 2. We're not going to worry about that right now. Okay, so this reaction occurs. This is more likely to give up electrons. Okay, so this reaction does occur. Whoops, let's go to the copper. Okay, you see how we use the table for that? All right, with my last 3 minutes here, I want to talk about one more reaction here. And then I'll leave this for you to practice on the homework. And this is reactions of metal with water. So metals can react with water, and they're essentially going to give their electrons up to water. And like I said, sometimes these things are so reactive that they will give up their electrons to just pure water, and sometimes you need to have a little bit of acid around. So an example of this is sodium metal. If you take that and throw that in water, okay, what will happen is you will get sodium hydroxide plus hydrogen gas. Right, this is not a balanced equation at the moment. This is going to be aqueous. This is going to be liquid. All right, I'm not going to bother balancing these for the moment. You should be able to balance this sort of thing. Yeah, I'm not going to worry about that for the moment. Okay. So that's one reaction that can happen there. All right, but so what's going on here is our water is breaking up into hydroxide, okay, and the H2. And that is a reduction reaction because if you think about the water breaking up, we end up with an H plus, and then it gets an electron, so it can make H2, which is neutral. All right, another example of this. We could talk about lithium as well, but the same sort of thing. So I guess what I'll do is I'll balance these to finish things off for the day. Lithium plus lithium hydroxide plus H2, same thing. And so this is when I talk about having done these reactions and shot things up into the ceiling and things being on fire. What's going on is these reactions make hydrogen gas, which you can light on fire, and they're producing a lot of heat at the same time to try and start things on fire. Let's go ahead and balance this thing real quick. So I've got 1 sodium on each side. I've got 1 oxygen on each side, right? So I would balance this by adding I've got 1 oxygen on each side, right? So I balance this by I've got 2 hydrogens over here and 3 hydrogens over here. So that's not going to work. It's going to be complicated. It's going to be ugly. Actually, I can balance it like this. If I do this, right? If I make that a half, now it's balanced. And then I have to get rid of my half, so I would rewrite it as Na2. I'm going to multiply everything by 2 across the top. Plus H2 gas. And now it should be balanced. 4 hydrogens, 4 hydrogens. Okay. All right, any questions? All right, well, you guys have a good couple days. Remember, we have our quiz, and I've got hours this afternoon if anybody wants to stop by and practice things. I'll have that help session on Thursday evening.